Thermal radiation is often taught as the first scientific problem that exposed the breakdown of classical physics and required an explanation grounded in quantum mechanics. The thermal radiation theory provides a foundation for irradiative energy levels of a thermal emitter, which refers to any object in the universe that has a defined temperature. I begin with a picture of a galaxy from the Hubble Space Telescope. Each of the billions of stars in this photo has a distinct temperature and associated spectrum. As we have seen, Maxwell's theory of electromagnetism predicts modes of radiation using a spherical model for the emitter, but does not put any limitation on the possible frequencies. It makes sense to propose a spherical geometry that defines the modes of radiation emitted by heavenly bodies because stars, planets, and moons are spherical, to a good approximation. However, classical theory does not explain the spectra of stars. Planck combined the concept of quantized radiation levels of energy n times h nu with the classical theory to arrive at an accurate physical description of the emission of stars as a function of their temperature. To understand the fundamental justification for quantized electromagnetic radiation, we will briefly examine the classical theory and then contrast it with the quantum approach. The classical theory of thermal radiation was derived by considering a sphere with a temperature constraint at the boundary. Thermal modes of radiation, known as cavity modes, are in equilibrium with the temperature at the boundary. The figure shown here represents the wave vectors of allowed cavity modes in a spherical geometry. They are allowed because constructive interference is supported by an integral number of wavelengths in the sphere. We have seen in Podcast 1 that the classical theory predicts a continuous set of modes that satisfy the boundary conditions. But this theory fails to explain the spectra of stars and planets. At the turn of the 20th century, scientists knew that the classical solution made no sense. It was theoretically unreasonable that the spectral irradiance would increase without bound as the wavelengths got shorter, or the frequency increased. This implies also that objects emit at infinite power, which is also unreasonable. A drastic change in approach was required. To explain thermal radiation emitted by celestial spheres, a further constraint is required, namely that the radiative modes have discrete levels with a spacing given by a constant called h, Planck's constant, times the frequency. The very idea that electromagnetic waves have quantum levels implies that radiation may exist as a discrete object, a particle. Emission of radiation implies a transition from one level of the energy ladder to a lower level. The energy must leave as a packet, which means that it must leave as a particle, called a photon. The experiment that demonstrates the particle-like property of light had already been published, but was waiting for an explanation. Indeed, the introduction of the concept of quantized radiation was sufficient to arrive at a reasonable solution to the long-standing problem of thermal radiation. The spectral function known as the Planck distribution is a bounded function, as required. It has a maximum that shifts with temperature and an area that is dependent on the fourth power of temperature. It took Einstein only 3 years to realize a further implication of Planck's theory. Planck published in 1902, and Einstein's application of the theory to the photoelectric effect was published in 1905. Today, it is perhaps not a huge leap of intuition to see quantized radiation imply that light is also a particle. However, seeing that for the first time was Einstein's insight that won a Nobel-prize. Einstein saw this connection in a completely different type of experiment than Planck had considered to arrive at a quantized radiation theory. Einstein made a connection between quantized radiation and the absorption of light by metals to eject electrons. The ejection of conduction electrons by light had been given the name the photoelectric effect. The photoelectric effect was not explained by classical electromagnetism. The ejection of an electron requires that the energy input must be greater than a threshold value. Today, we see this readily as the requirement that a photon must have at least the minimum energy needed to extract or eject the electron from the metal. The work done to eject the electron is known as the work function. In atoms and molecules, the energy required to eject an electron is called the ionization potential, or the ionization energy. The analogous energy in metals is called a work function. The basic concept of extracting an electron is the same, but the work function is technically the minimum thermodynamic work required to remove an electron to a point in vacuum immediately outside the metal. The work function is a surface property and depends on impurities and imperfections in the surface structure as well as the type of metal. Both ionization and the photoelectric effect may be driven by light. Conceptually, they are very similar. Classical physics failed to explain the observation that a threshold frequency is required to eject an electron from a metal by light. In other words, it's not the intensity that matters, but the frequency. If the light that impinged on the metal was below the threshold frequency, no electrons were emitted, no matter how strong the intensity of the radiation. This is shown in this figure for the 700 nanometer red light. If the photon energy is lower than the plasma frequency, it should be reflected, which is often the case since the plasma frequency of most metals is quite high. Once one accepts the intuitive leap that quantized light can act as a particle, one can see the photoelectric effect as the effect of one particle, a photon, being absorbed, while another, an electron, is emitted. Since the particle's energy is proportional to frequency, E equals h nu, an electron will be ejected only when the threshold energy for emission has been exceeded. The yellow-green light, shown here, is above that threshold. In this case, the photon has slightly greater energy than the work function. The excess energy of the photon is converted into kinetic energy. The blue photon will photoeject an electron from potassium with greater kinetic energy than the yellow-green photon. This also means the velocity of the ejected electron increases relative to yellow-green light. In this example, potassium has a work function of 2 electron volts. A photon of red light in the diagram has an energy corresponding to 1.77 electron volts. It is below the threshold of 2 electron volts, and red light has no effect on the surface of potassium. It is reflected. The yellow-green photon has an energy corresponding to 2.25 electron volts, and the blue light corresponds to 3.1 electron volts. Here we see the equation used to relate the photon energy, work function, and kinetic energy. In the example above, the excess energies of the yellow, green, and blue light are 0.25 eV and 1.1 eV, respectively. I should comment that EV is not really a measure of energy. It's proportional to energy, but we often use it in this sense just because we know what the proportionality is, and I'll talk about that on the next slide. The velocities of the ejected electrons are given in meters per second. To solve practical problems involving the photoelectric effect, we need to consider unit conversions and use the mass of the electron to obtain the velocity from the kinetic energy. The work function is called phi, and it is usually measured in electron volts. The threshold for photoejection occurs when the photon energy, h nu, equals phi. If h nu is less than phi, nothing happens. If h nu is greater than phi, any excess energy is carried away as kinetic energy, shown in red. The energy in h nu has units of joules. To convert to electron volts, we simply divide by the charge of an electron in coulombs. Coulombs times volts equals joules. When a photon has excess energy, the photoejected electron carries the excess as kinetic energy. The work function and the photon energy are often given in units of electron volts. We can convert back to joules simply by multiplying by the electron charge. The electron volt is essentially the same as a unit of energy. To convert to joules, we simply multiply by the electron charge. 1.602 times 10 to the minus 19 coulombs. Solving a practical problem is the best way to understand the quantitative relationships of the theory. This typical photoelectric effect problem states that 250 nanometer light impinges on aluminum. It is implied that the energy of a 250 nanometer photon is greater than the work function. The energy of the photon must be greater in order to tear loose an electron from the metal. The question posed is how much excess energy the electron has, although it is framed in terms of calculating the momentum and velocity. Work functions in units of eV are given in tables that are easy to find on the web. The work function of aluminum is relatively low compared to many metals. It is 4.1 eV. The difference between the incident photon and exiting electron in electron volts is proportional to the kinetic energy. To convert from 250 nanometer wavelength to units of electron volt, or eV, we must divide the energy expression by the charge on an electron in coulombs. Using the known values of the constants, we find that the incident photon energy corresponds to 4.9 eV. Therefore, the ejected electron carries away 0.8 eV that can be converted into its kinetic energy. Finally, we can insert the values from the previous steps and calculate the momentum. You might wonder why we bother to calculate momentum. In future podcasts, we will show that the momentum of a particle is extremely important in the so-called wave-particle duality. The velocity of an ejected electron is readily calculated from the momentum as well. To put the velocity in terms we are familiar with, a jet traveling at 1,000 kilometers per hour has a velocity of 277 meters per second. The ejected electron travels 2,000 times faster than a jet plane.